Hello everyone, welcome to this lecture. So, in this lecture we will see that the condition t less than n by 2 is a necessary condition for designing any generic MPC protocol. Namely, we will show that there exist some functions which we cannot securely compute if the number of corruptions in the system is not upper bounded by n over 2. Remember, we have shown that if we have a linear function, then the linear function can be securely computed even if up to n minus 1 corruptions are there in the system. What we are going to show here is that there exist some functions, there are some functions for which we require this much condition, this condition to be necessary. Okay. So, before going into the proof, let us first recall the GRR degree reduction method and try to understand that where exactly it will fail if we do not make the assumption that t is less than n over 2. So, the inputs for the GRR degree reduction method are two values a and b which are randomly t shared. The parties compute locally the product of a shares and b shares that will collectively generate a vector of shares lying on a 2t degree polynomial. And then we argue that the constant term of this k polynomial, which is a b, can be expressed as a linear combination of this k1 value, k2 value, ki value, kn value, provided n is greater than equal to 2t plus 1. Okay. Because the degree of this k polynomial is 2t and this k polynomial is uniquely determined only if n is greater than equal to 2t plus 1. Because remember, this k polynomial is a polynomial passing through alpha 1 k1, alpha 2 k2 and alpha 2t plus 1 k 2t plus 1 and like that alpha n k n. So, only when n is greater than equal to 2t plus 1, whatever we are writing here makes sense. Okay. And then assuming that n is greater than equal to 2t plus 1 or t less than n over 2. So, this condition also means t less than n over 2. Assuming that that condition is ensured, then the parties can secret share their respective k values. So, we can ask P1 to do this, we can ask Pi to do this, we can ask Pn to do this. Do this means secret share individually their k shares, and then we can apply the public Lagrange linear combiners and obtain the random vector of C shares lying on a t degree polynomial. So, now what goes wrong if we do not ensure that n is greater than equal to 2t plus 1. If n is not greater than equal to 2t plus 1, then whatever we have written down here, that is not correct, because this k polynomial, it has degree 2t. So, we need 2t plus 1 distinct points to uniquely determine this k polynomial, and hence we require 2t plus 1 distinct points to uniquely express a b, a times b as a linear combination of those 2t plus 1 distinct values, right. If n would have been say just equal to 2t, right, there are only 2t number of parties in the system, then this linear combination trick will not work, because I cannot write a b as a unique linear combination of those 2t number of k values, and hence we cannot say that this vector of shares C shares lie on a random t degree polynomial whose constant term is a b. Its constant term need not be a b, right. So, that means definitely for the GRR degree reduction method we require t to be strictly less than n over 2. But that does not mean that every other degree reduction method also requires t less than n over 2. There might be a clever way of doing a degree reduction, or first of all there might be a completely different approach of securely evaluating multiplication gates, which need not be based on shared circuit evaluation, some other approach which may not require this t less than n over 2 bound. What we are now going to see is that that is not the case. There exist some functions which we cannot securely compute if there are more than half of the participants who are corrupt. So, what we will do here is the following: we will show that there is no perfectly secure two party protocol for computing AND of the bits of the two parties if one of them is passively corrupt. Namely, the setting is the following: we have two parties here, party 1 has the input bit B1, party second party has input bit B2. We require a method which allows the parties to finally learn the AND of their respective bits, but in this process the view of, and one of these two parties could be corrupt by a computationally unbounded adversary, and we want that a protocol should ensure that a view of the corrupt party should be independent of the other party's input. Namely, through the function output and the input of the corrupt party, nothing additional should be revealed about other party's input. So, what I mean to say here is that if B1 would have been 1, if B1 is equal to 1 and y equal to 0, then of course, other party's input is learnt, right. That is not a privacy breach, definitely that leaks B2 equal to 0, that is fine, that is acceptable, because that is anyhow inferred from the, if P1 would have been corrupt, then anyhow just based on its input and function output it could easily conclude what is the other party's input, that is not privacy breach. What we want here is if B1 is equal to 0, then definitely y is equal to 0. Then we want that if P1 is corrupt, then whatever is view 1 that is generated in the protocol, that view 1 should be independent of whether B2 is equal to 0 or whether B2 is equal to 1. That is what the protocol should ensure. Okay. So, we are arguing here, we are going to show here is that there is no such protocol possible which gives you these guarantees. That means, the theorem statement that we are going to prove here is that there exists no perfectly secure protocol for securely computing the two party AND function, and the proof will be by contradiction. We will assume that, on contrary there is some abstract protocol pi, okay, according to which the parties can exchange messages and finally they obtain the AND of their respective bits and it satisfies these conditions. That means, you can imagine that abstract protocol pi. By the way, pi need not be just secret sharing based protocol, it could be any abstract protocol. We are trying to rule out the possibility of any kind of perfectly secure protocol. So, it could be based on secret sharing, it could be based on any cryptographic primitive. We are going to abstract out that protocol. The way we are going to abstract out the protocol is as follows. So, we will assume that the protocol pi will have the following form, and this form is a very generic form, it captures any kind of two party secure protocol that you can think of. The protocol will take the respective inputs of the parties, and of course, the protocol has to be randomized, namely the messages which parties are going to exchange, they have to be random messages, they can't be fixed, they can't be just based on the inputs of the parties, because otherwise that clearly is going to breach the privacy of the inputs of the honest party. Okay. So, there will be some internal randomness, random strings which are produced by the parties, generated by the parties during the execution of the protocol, and based on the inputs and based on the input and respective randomness, the parties start computing messages as determined by the protocol pi. So, they are not going to send arbitrary messages, they are the messages which they are now going to communicate. It will depend on the value of the input, the internal randomness and the steps of the protocol pi. Okay. That means, if the value of B1 is fixed, but the randomness changes, then based on the steps the value of the message M11 will be different and the value of M12 which P2 will send back will be different and so on. Okay. So, assume that the protocol is an S round protocol. Of course, the number of steps or the number of times the parties have to interact, that will be publicly known, that is not an unknown quantity, that is publicly known, because we are assuming that the steps of pi are publicly known. And then finally, based on whatever messages the parties have exchanged, the parties, respective parties obtain the function output, which is the AND of their individual bits. Now, this highlighted thing, namely the messages which parties have exchanged, I call it as the protocol transcript. Okay. Namely, whatever values messages P1, P2 have communicated, the full thing that is now publicly known, because whatever P1 is sending to P2, that is known to P1 as well as to P2, and whatever P2 is communicating back to P1, that is known both to P1 and P2. So, this transcript is publicly known, and this transcript is a random variable, remember. Why it is a random variable? Because even if the same two parties execute the protocol pi with the same value of B1 and B2, depending upon what exactly are the random coins which parties are using during the run time of the protocol, that will determine the messages M11, M12, MS1, MS2, and that is why these messages are not going to take fixed values, they are going to take different values with different probability, which depends upon the value of the internal randomness. So, that is why this transcript tau is a random variable. Okay. So, now let us introduce some notations here. Let this fancy T and input B0 B1 denotes the set of all possible transcripts which the protocol pi can generate if the two parties would have participated in the protocol with inputs B0 B1. Okay. And this is a finite set, remember. Why finite set? Because as per the steps of the protocol, there are only finitely many random coins which P1 and P2 could generate, and if we now execute all possible executions of the protocol pi by fixing B1 and B2 and with different candidate R1 R2, we can generate this entire set of transcript. This might be enormously large, it could be exponentially large, that is fine. Exponentially large means it might take exponential amount of computation to generate that set, that is fine, but that is finite, that is not an infinite set. And an adversary who is computationally unbounded, it can always generate this entire set of transcripts. Why? What it has to do? It just has to run the steps of pi in its mind, assuming that the inputs of the parties are B0 B1, and just by changing randomness component, it can reproduce all the transcripts and then list it out, and that will be this set fancy T form. Okay. And now let fancy T be the set of all possible transcripts that can be generated for all possible input combinations of the parties. So, of course, this it is a bigger set, it is a universal set of transcripts which the protocol pi could generate. Okay. So, now we are going to argue some properties regarding the distribution, the nature of transcripts which the protocol pi can produce, and then based on that we will finally rule out that definitely the protocol pi breaches the privacy property, and hence we will conclude that whatever we assumed regarding the existence of the protocol pi, that was incorrect. So, the first claim is that there is no transcript possible which can be generated if the inputs of the parties would have been 0, 1 and if the inputs of the parties would have been 1, 1. That means, the set of transcripts which can be produced by this input combination, that is completely disjoint from the set of transcripts which would have been generated in this input combination, and this could be argued very easily. If you see closely here, the output, the function output for the case where the inputs of the parties would have been 0, 1 is 0, and the function output which should have been generated if the parties participate with this input combination should be 1. That means, the function outputs are different, and your transcript determines the function output as well, because the final output is decided based on whatever messages the parties have exchanged till now and the steps of your protocol pi. That means, there will be a final output determination step of the protocol pi, which should say that okay, if these are the things which you have seen till now, then output this, right. So, how can it be possible that the same output decision step for this case as well as this case outputs the same value? That can't be possible, because we are trying to argue here that there can't be a transcript tau which is a member of both this input configuration as well as this input configuration. On contrary, assume that there is such a transcript tau which is member of both the set of transcript for the 0 1 case as well as for the set of transcript, as well as it is a member for the set of transcript for the 1 1 case, then the same transcript tau should tell that okay, generate the output 0 as well as generate the output 1, which is a breach of the correctness property, because we are assuming that the protocol pi gives you absolute correctness and absolute privacy. Okay. That is what we are trying to argue here. We argued that there exists a perfectly secure protocol, and as part of perfect security we also assume perfect correctness. There is no error in the protocol output. That means, there can't be a member, a transcript which can be generated both for this input combination as well as for this input combination. They are disjoint members, an obvious fact. Okay. The other claim regarding the set of transcripts is very subtle. My claim is that the set of transcripts which could be generated for the input combination 0 0 is exactly the same as the set of transcripts which would have been generated for the input combination 1 0. That means, this means that if there is some transcript tau belonging to the set of transcripts for 0 0, then it also belongs to the set of all transcripts in 1 0 and vice versa, of course for different randomness. Okay. How we prove this? On contrary, suppose this claim is not correct. What does that mean? That means, there is some transcript, some bad transcript, let me call it bad transcript tau prime, which can be generated for input configuration 0 0, but it can never result if the parties have their respective function inputs as 1 0. And if this is the case, then we will argue that the protocol breaches the perfect privacy. But since the protocol is perfectly secure, it has to satisfy the perfect privacy, and hence this claim is indeed correct. So, let us see how exactly we prove this claim, assuming that this claim is not true, how exactly we arrive at a contradiction. So, imagine there is a bad transcript which can never result if the parties participate with inputs 1 0. If that is the case, and suppose that transcript tau prime results when the randomness of the parties are R1 and R2 or R1 and R2 prime say. Okay. So, that means assume a scenario where P2 is corrupt, right, and it participates with input 0, P1 has participated with input 0. Of course, the set of messages which are communicated is tau prime, the bad transcript, and of course, the function output is 0, because both the parties have participated with input 0. Now, if tau prime constitutes a bad transcript, then a corrupt P2, if it sees that okay, the messages which are exchanged as per the protocol during the execution is tau prime, then it can easily infer that the input of the other party is 0, it is not 1, because if it is computationally unbounded and if it knows that there is such a bad transcript tau prime, which can be present in the set of transcripts with 0 0, but it can never be present in the set of transcripts with 1 0, and if indeed during the execution of the protocol the same transcript tau prime ends up, then P2 knows that okay, I have actually participated in an execution where the input of other party is 0, it can't be 1, which is a breach of perfect privacy, because if indeed protocol pi satisfied the privacy property, then this transcript tau prime could also result for b equal to 1 and some candidate randomness r 1 double prime. But that is not the case. We are assuming here that there is no possibility that this transcript tau prime could also result if the input of P 1 would have been 1 and he participated with some other randomness r 1 double prime. That is what we are assuming when we say that this transcript tau prime is not present in this set. That means if B 2 is equal to 0, r 2 prime is fixed, there can't be possible, it can't be possible that B 1 equal to 1 and randomness is r 1 double prime, where the set of messages which P 1 would have sent is actually the same messages are actually the same messages which P 1 has sent as per the transcript tau prime. That is what we are assuming here. Okay. And if this is the case, then indeed if P 2 participates in the protocol with B 2 equal to 0, and if indeed the transcript tau prime is the resultant transcript, again the probability of happening this is might be less. It depends with if this transcript tau prime can indeed occur only if P 1 is also participating with randomness r 1 prime and P 2 is also participating with randomness r 2 prime with their respective inputs being 0 0. Only in that case this transcript tau prime could be generated, right. The probability that the respective randomness of P 1 and P 2 or r 1 prime and r 2 prime might be very small, it might be negligible, but that is a non-zero probability. So, what we are arguing here is that if this claim is not true, then there is always a non-negligible chance that P 2 is a lucky guy who ends up seeing the protocol transcript tau prime, and if indeed she is lucky and sees the protocol transcript tau prime and her input was B 2 equal to 0 and randomness was r 2 prime, she can easily infer that she has seen or she has participated in a protocol execution where B 1 was 0 and not B 1 was 1, and that is a breach of privacy. That is why this claim is also true. So, I have written down these two claims. So, assuming, so what we have done till now, assuming pi has perfect correctness and privacy, we have shown that these two properties must hold. Now, based on these two facts, we will see an adversary strategy which can allow a corrupt P 1 who participates in the protocol execution pi with B 1 equal to 0 to analyze the protocol transcript and come to the infer and find out what exactly was the input of the other party with 100% probability. Okay. So, consider an execution where now P 1 is corrupt, it participates with input B 1 equal to 0 and of course, its randomness is r 1. It does not know whether input B 2 is equal to 0 or input B 2 equal to 1. We are now going to see a strategy which will allow P 1 to analyze the transcript tau based on these two facts and come to the conclusion that whether it has participated with B 2 being 0 or B 2 being 1, which will be contradiction to the fact that protocol pi has perfect privacy. So, here is the strategy of P 1. P 1 once the protocol is over, anyhow it will learn that y is equal to 0. It now starts building a table, various tables in his mind. He checks in his mind that is it possible that the messages which have been exchanged in the protocol, namely this concrete transcript tau, is consistent even with B 1 equal to 1 as well. Okay. What does that mean? That means he is now built several incomplete transcripts where the messages from P2 has been fixed as per tau, because that is what he has seen, right. And this is a similar exercise which we have done for our secret sharing based protocols, where a corrupt party, he fixes whatever he has seen and put question mark with respect to what could be the candidate input of the other honest parties, and try to fill those candidate inputs and see whether that matches with whatever the adversary has seen. That is what we are doing here. He is trying to check whether the same transcript is consistent with B1 equal to 1 as well. That means P1 in his mind, he has participated in the protocol with B1 equal to 0, and that has produced this transcript tau. Now he is doing an exercise in his mind, he is trying to change his input to B1 equal to 1 and trying different candidate randomness, and for this changed B1 and candidate randomness, he is seeing that whether the protocol pi would have produced the messages M11, M21, MS1 from P1 being sent to P2. He is not changing the messages from P2, that is fixed, remember that is fixed to M12, M22, MS2, namely all the round messages which P2 would have communicated as per tau, that is fixed. P1 is basically just changing his input and his randomness and communicating messages as per protocol pi, and seeing whether the messages which he would have sent as per protocol pi with the changed input and changed randomness are consistent or the same which tau has. Okay. So, if it is not satisfied with first candidate randomness, then it goes to the second incomplete table, where again the messages from the second parties have been fixed, and he has changed his input from B1 equal to 0 to B1 equal to 1, and now tries another candidate randomness and tries to fill those missing messages and check whether that is equal to tau or not. If it does not, then it tries the next candidate randomness and so on, and there are only finitely many candidate randomness. Of course, it could be exponentially large, but remember we are considering a strategy for a potentially computationally unbounded P1. So, it can run through all candidate randomness and fill all the incomplete tables. Finally, after filling all the tables, P1 comes to the conclusion that other party's input was 0 if by doing the above exercise he can find a candidate randomness such that that candidate randomness along with B1 equal to 1 would have produced the same transcript tau. Otherwise, he says or he infers that I have participated in the protocol where B2 was 1. And why this strategy will work? This strategy will work because of these two claims, okay, right. If indeed B2 was 1, if indeed B2 was if indeed B2 was 0, take the case if indeed B2 was 0, then we know that if and that means this tau belongs to the real transcript tau that has been produced in the real execution actually belongs to the set of all transcripts 0 0, then as per this claim it should also be produced if P1 have participated with input 1 and with some other candidate randomness. Okay. Whereas, if this tau would have been a member of a set of transcripts where the input of party P2 would have been 1, then as per this first claim the same transcript tau can never be a member of the set of transcripts where the input of the first party would have been 1, another party's input would have been 1, and that is what precisely P1 is doing here. So, based on whether this exercise in P1's mind is successful or not, it can easily find out by analyzing the protocol tau whether the other party's input was 0 or 1, which is a contradiction to the perfect privacy of the protocol pi, and that shows that we cannot design a secure two party AND protocol. Okay. Now, we want to generalize this argument to argue that if there are n parties, okay, with their respective private bits B1 to Bn. Okay. And if we want to securely compute the AND of those n bits, and up to t of the parties could be corrupted by the computationally unbounded adversary, and if we are in the setting where t is less than greater than equal to n by 2, then there exists no secure protocol to securely compute the AND of the n parties, AND of the bits of the n parties. And how exactly we are going to do this? We are going to show it, we are going to show the proof, prove the theorem as per as follows. So, we will assume that we will show that if there exists a protocol for securely computing the AND of n parties where n is equal to 2 t. I am taking the case where n is equal to 2 t. Of course, t greater than equal to n by 2 means n can be less than 2 t as well, but I take the largest possible value of n satisfying t greater than equal to n by 2, namely n is equal to strictly 2 t. Okay. So, I will show that if there is a protocol for securely computing the AND of 2 t number of parties where even up to half of them can be corrupted by a computationally unbounded adversary, then using that protocol we can design another protocol which can allow 2 parties to securely compute the AND of their respective bits. But we already know that this no such 2 party protocol is possible. That means, no such 2 t party protocol is also possible. That is what we are going to do. So, assume there is some hypothetical protocol for 2 t number of parties, assuming n is equal to 2 t, which is secure even if up to half of them can be corrupted. That means, even if any set of t parties get corrupt, the view that this protocol generates for those t bad parties, that view will be independent of the inputs of the remaining t parties. That is what is the privacy property of this protocol pi 2 t comma t. Okay. Now, using this protocol we will design our 2 party AND protocol. In the 2 party AND protocol, I am taking the parties to be P A and P B with their respective input bits being 0 A and B respectively. Now, the protocol code of pi is publicly known. So, what P A can do is the following. P A can think in its mind that it is going to play the role of first t parties P 1 to P t as per the protocol pi, assuming that all their input bits are A. Okay. It can do that, and party B can do the following. It can play the role of the remaining t parties as per the protocol pi 2 t. So, we are assuming that there are 2 t number of hypothetical parties, A is playing the role of half of them, B is playing the role of half of them. That is the protocol gamma here, the 2 party AND protocol. A is playing the role of t parties as per the protocol pi, assuming that all their inputs are this A, the bit A for the 2 party protocol, and B is playing the role of another set of disjoint t parties as per the protocol pi, assuming that all their inputs are B. Okay, that is a protocol pi. That means, if protocol pi has instructions for party number P 1, party number P 2, party number P I, party number P n, assuming that their bits are B 1, B 2, B I, B n, right. That is what will be the protocol pi, right. It will have instructions for P 1, it will have instructions for P 2, it will have instructions for P I, it will have instructions for P n. What I am proposing here is the following. In the protocol gamma, which is the 2 party protocol, party A takes the instructions of first t parties that are instructed as per the protocol pi, and he is going to run those instructions, assuming that t parties are participating with input 1 with input A as per the protocol pi, and party P B is going to run the instructions of t plus 1th party, t plus 2th party and the 2tth party as per the protocol pi, assuming that their inputs are the bit P. Okay. Now, if in the protocol pi some interaction is involved between any party in this collection and any party in this collection, then whatever messages they are supposed to communicate, PA and PB will communicate in this two party protocol. Whereas, if in the protocol pi, if there is any communication from any party in this group to any party within the same group, that will be treated as if PA is communicating that message to itself. So, the idea here is basically whatever communication the parties n 2T parties would have done as per the protocol pi, the same communication PA and PB are emulating, by dividing the role of the 2T parties among themselves. Whenever there is a requirement of communication within this group among this group and this group, PA and PB will communicate, otherwise they will not communicate. That is the protocol gamma. Okay. So, it is easy to see that the final outcome, if the protocol pi satisfies the correctness property, then gamma also satisfies the correctness property, because the output of the protocol pi would be the AND of the bits of 2T parties, and the AND of the emulated 2T parties are here A and B. So, the correctness property is guaranteed, that means correctness of this protocol pi implies the correctness of this protocol gamma as well. Now, let us try to argue the privacy. Can I say that the privacy of this protocol pi also implies the privacy of protocol gamma? And the answer is yes. Why so? In the protocol gamma, it could be either the party PA or it could be the party PB who could be corrupt, because in the protocol gamma it is a secure two party protocol, there are no 2T parties. The role of T parties or the code, protocol code of T parties are run by PA and the protocol code of T parties are run by PB. So, there are only two parties. Okay. What will be the view of PA in the two party protocol? Well, it will be identical to the view of T parties, the first T parties that they would have generated in the protocol pi if all of them would have participated with input bit A, right. And what will be the view of this second party PB in the two party protocol? Well, it will be identical to the view of the last T parties if they would have participated in the protocol pi with input being B, right. That has come because of the way PA is playing or running the code of first T parties. That means, whatever random values the P1, P2, PT, PT would have been asked to pick, those random values PA would have been picked. If P1 would have been asked to secret share some value, PA would have done that. If P1 would have asked to communicate some message to P2, okay, P1 PA will say that okay, this is what will be the view of view 2, okay, and so on. So, this combined view of this first T parties in the protocol pi will be treated as the view of PA and same for PB. Now, what we know is the following: the combined view of first T parties as per the protocol pi should have been independent of the view of the remaining T parties if in protocol pi the first T parties would have been corrupt, right. Namely, what I am saying is that if P1 to PT gets corrupt in the protocol pi, so they will be having access to B1 up to BT, which in this case in the context of gamma protocol is all set to A, and they will be anyhow finally learning the output of all the remaining bits, okay, and of all remaining bits. So, the final outcome is also consisting of BT plus 1 and BT plus 2 and B2T. That is also learnt as part of the final outcome. Now, can I say that if P1 to P2 gets corrupt, they conclude they learn any additional information about the exact bits of the remaining T parties in the protocol pi? No, the remaining T input bits of the remaining T parties in the protocol pi could be any combination It could be the case that all of them are the same bit or they are different bits depending upon, just that it has to be ensured that finally the AND of those remaining t bits along with the AND of the t bits of these t parties should produce the final outcome which the pi protocol should have produced. So, translating it to the context of the gamma protocol, I can say that the view P A which the protocol gamma would have generated in case if protocol P A is corrupt will be independent of B t plus 1, B t plus 2 up to B 2 t. That means, even a possibility of all of them being B is possible, or all of them or some of them being B and some of them being B prime, that is also possible. All of them are equiprobable. That means, if P A's input would have been 0 say, that means it would have run all the first t parties with input 0 and it would have learned the final output to be y equal to 0. Now, based on this it can't rule out whether the inputs of all the remaining t parties are 0, or it can't rule out that the inputs of some of them are 0 or some of them are 1 and so on, because that is coming from the privacy property of pi. That means, y being 0 and the input of first t parties being all zeros as per protocol pi, that view could also be produced, the view that is produced there can also result equiprobably from the case when the inputs of all the remaining t parties would have been 0 or half of the remaining t parties have participated with input 0 or with input 1 and so on. That means, in the context of this translated protocol gamma, I can say that the view of the party P A is completely independent of the actual bit B, whereas if P B would have been corrupt in the protocol gamma to 1, then since its view is identical to the view of last t parties, and if the last t parties would have been corrupt in the protocol pi 2 t, its view would have, their view would have been independent of the view of the first t parties, and the view of the first t parties in this gamma protocol is basically the depending on your bit A. So, that means I can say that the view of the party P B, if it would have been corrupt, is independent of the bit A. So, that is why this implication, namely the privacy of the protocol pi translates to the privacy of the protocol gamma is correct. That means, if at all I have this protocol pi 2 t comma t, I can design a protocol pi gamma 2 comma 1 by doing this exercise, A copying or running the code of first t parties, B running the code of last t parties, and that is whatever messages are supposed to be exchanged as per the protocol pi, they exchange messages among themselves depending upon the messages are supposed to be exchanged within the group or between the group. But we know that no such protocol gamma is possible, hence no such protocol pi is possible as well, and that shows the optimality of this bound for certain functions. Okay. So, the proof of the impossibility of secure two party and this reduction from the two party to the generalization of the two party impossibility to the n party impossibility has been taken from this book. Thank you.